Thank you, Chrissy. So we've got 15 minutes. I presented this last week in 20, so buckle up. We're going to make this as fast as we can. So we'll blast through some things, and I really want to spend some time on the proposition, where our products go, rather than dwelling too much on project and all that kind of stuff. So apologies if you wanted to get into that. Happy to chat later. So we are a technology-driven specialty chemicals business. We have a novel technology that uses solvent extraction to purify aluminium, and that aluminium is used in chemicals that are used in the high-tech sectors of semiconductors, LED, EV batteries, and so on. So sort of all of those future-facing commodities that we've been talking about. We have a project that is commercialising that technology called the HPA First project in 2 stages. Stage 1 is in production. It's a small-scale commercial sort of facility that is also servicing large quantities for technical qualification. And then stage 2, which is in production, which we'll get into in a sec. So that's stage 1. It's situated in Gladstone, which is in sort of central Queensland on the coast. And you can see Orica, which is one of our business partners and suppliers, a reagent supplier, and Rio in the background, which supplies our raw material. Orica is also a 5% stakeholder in the business and joined the register right after we started up stage 1, which I think was a significant endorsement in the technology itself. This gives you a sense of scale of what's going on inside the facility. We've got Alex there running the SX in the top left-hand corner. And then that picture there of the product is actually a 1-ton order that we set aside for a Korean semiconductor business where we ship that material to. This is actually what we're building now. It gives you a sense of scale in terms of where stage 1 is in the yellow box, and then stage 2 is obviously the large facility there. And we're actually interconnected with Orica because the reagents that we use with Orica and then send back to them are just connected across. So we actually are responsible for about 20% of Orica's output. CapEx is 553 million, and I just would say that His Excellency's comments around those various government funding opportunities, we are sort of pretty much fully loaded into all of those. The Critical Minerals Fund, etc., is all part of that funding package from EFA and NAIF. That's what we're building. The project's on time and on budget at the moment. Excavations are finished, and we're getting into civils in the next sort of quarter and a half. So a little bit about what the products are doing. We really are sort of leaning into some of these AI data center piece. So just a little bit of a driver for what's impacting AI data centers and so on is obviously the power. 40% of the power at these facilities is for cooling, and that's where our materials come in. So our material is very unique, and I think the common thread that you'll see through all of this is that we are leaning into sectors in these markets where our material outperforms everybody else's. So that's where we really compete, and that's where the business really shines. And this is all enabled by our technology. If there's any uranium and thorium fans in the room, you're going to be very disappointed because we ain't got none. It's not in our material, and that's why it outperforms in these semiconductor applications. In particular, this one, which is quite interesting, uranium and thorium emits what's called, this is a physics lesson for you, alpha radiation. Alpha radiation is a particle, and it will knock electrons off a circuit, right? So think of, this is my mechanical engineering brain trying to explain something very complicated, but basically when that happens, it causes an error in the performance of the AI chip, and our material, when applied in these thermal fillers to reduce the heat, extract heat away from the circuit, does not impact the performance of the chip. So it actually allows the chip to perform more efficiently, and we have confirmed from some of the largest companies and best, well-reputable companies in the business, in Japan and so on, that it is the best material in its class. And so this is something that is directly enabled by our technology. You'll see a theme around this as we keep going. The next one is the CMP polishing. So CMP polishing stands for chemical mechanical planarization. Our technology is producing an alumina, that high purity alumina, that just outperforms in terms of the way it polishes the wafer. So that little image there looks sort of like a wacky record player. That actually has the little orange piece there has the wafer on it, which the silicon chip is the chip is grown on, and specifically we're talking about chips that are in the silicon carbide substrates, the sapphire substrates, and the gallium nitride, and these are all power semiconductors. Power semiconductors are a key element of the sort of energy transition. So any piece of equipment that's controlling high power, amperage, voltage, etc., such as an EV power battery, an EV battery pack, solar panels, wind generations, all that kind of stuff is where these special semiconductors land, and so there's a significant demand for these. And I should say that in relation to the semi market, we are seeing continual expansion in the demand for our products in this space, irrespective of what you may or may not speculate in relation to the impact of DeepSeek and all those other things. So what we're seeing in real terms on the ground is that the demand for this material and the material for the thermal interface packaging is continuing to rise, and we've got LOIs in place that are being revised upwards in terms of their tonnage. And so our crystal morphology from our technology again outperforms others in this sector, and so we've actually got a 4,000 tonne LOI in place just recently for this material as well. So the CMP process is a process of polishing the wafer using the slurry, and it's an ongoing thing as they build out the lithography of the circuit. It's just an ongoing, they have to put it back in, polish it off, remove the material they don't want, and so on. So it's an ongoing process that they use. We also make batteries safer, and we do that because one of the materials that drops out of our circuit, out of our technology, is a material called aluminium nitrate, and I'll give you a quick Cook's tour of that in a minute. But the aluminium nitrate is something that we've solved for, in that we can produce aluminium nitrate at a very, very high purity, like 99.9999%, at a commercially viable cost. Has been a technology out there for a while there's some PhD papers written on this around how you could use aluminium nitrate to use it as a coating on an anode in an EV, and so, but this technology sort of sat on the shelf since the mid 2010s because there wasn't a commercially viable sort of material like the aluminium nitrate material to be used in that application. You need the purity. It's a very challenging process to produce using traditional methods. So we've come in and we've solved that. We're working with about 14 counterparties in this regard, and we're also working with one of the biggest anode producers in the world on this. And it all ends up all the material will ultimately end up in sort of tier 1 OEM type batteries. So we've gotten through technical qualification with this process. It's been sort of 18 months of test work that we've been doing with them so far, and now we're just sort of waiting for further updates from their end users, which is all part of the process. But a really, really interesting technology. And again, the same theme where it's our technology that's doing something that nobody else can, and that's where the value creation is coming from. And then the same again, we can do that same sort of process, but in terms of battery cell case coatings. So you can see here when you use our precursor to coat the inside of these prismatic cells, the image there with the blowtorch, which is actually a test that they do. It's not just something that we're noodling around like a couple of pyros in a workshop. That's actually a test with a 1600 degree butane flame, and then you can see with the aluminium sheet with no protection on it, it's sort of blasted through in sort of 15 seconds, but when we coat it with our material, it's lasted 9 minutes or so and still going. So the interesting thing about this is that it's sort of a net neutral cost in terms of the application, but it gives them more space in the battery, and because of the high purity of the material, it's inside the cell and it doesn't interfere with the chemistry of the cell. So we're actually working with a global automotive OEM on this technology, who are developing their sort of battery pack in-house. Then there's the DLE sector, which sort of leans into the sort of lithium piece a little bit, and so it's the technology that is enabling this and opening this up, but we make a material called aluminium hydride, or ATH as we call it, and it is best-in-class performance, again, both in terms of the strength. So when you're using a DLE, it's actually absorbing, or adsorbing is the word, onto the particle. So at a microscopic or sort of nanoscale almost, the lithium ions are getting trapped in the pores of the sorbent, okay? And that's just sort of like a pool filter, I guess, and then once you flush it through with clean water, you pick up the lithium and take it away. And so our material is performing 2 times extraction rates and lasting sort of 1.5 times more. So the efficiency there is really strong, and we're working with a number of counterparties and some big petroleum majors around this. And there's again, it's all in the morphology of our material and how we precipitate it that is enabling it to outperform. It's also worth understanding that this particular application in a DLE sorbent, 90% of the ingredient of that sorbent is ATH, is our material. The balance of it would be a lithium chloride and some other special synthesis that they do in how they produce the final material. But our material would represent 90% of the bulk ingredients for a final sorbent. Significant growth seeing in this market, and as a little sort of fun fact, if you think about the lithium triangle in South America, the existing salt flats, they could get a 35% uplift in their production, the lithium salt flats there, if they were to switch to DLE. And the difference is you get a 2-day turnaround on your yield as opposed to 18 months on the salt flats and the evaporation ponds. So quickly, how do we do it? We have an input material from Rio Tinto. We use for our full-scale facility, we use about 13,000 tonnes of that, and then Orica gives us our reagents. We put that through our solvent extraction circuit. We crystallise it, and that's where our first material drops out, which is the high purity aluminium nitrate. That is then a precursor for all the other things. And so particularly that front end is really where our USP is. And then the balance of it is sort of relatively common. And there's a lot of particle engineering that happens through that and a lot of know-how through that whole process. A little bit about product marketing and progression. We're working through LOIs, and then they'll ultimately convert to binding contracts. But you know, it comes back to how our material is delivering on areas where others cannot. And I really wanted to take a little bit of time to explain to you what an LOI really means for us. It's not like an LOI for the gas industry, which are thrown around like lollies. It takes a long time to get to an LOI. So a typical process, you can see we've got a target customer, there's a desktop review, and then small samples and then large samples. And that large sample process, there's a lot of back and forth, which is that sort of back and forth arrow there. I don't have a laser pointer, but you can see there in the middle. And that when the customer's happy with the performance, then they'll start sharing that with their customer. Then they've got that same iterative loop that can potentially happen with their customer. And then ultimately, once that's all satisfied, we go to product qualification. We get a product qualification letter, like I mentioned earlier, and then that is usually accompanying with an LOI. And then finally, the sales contract is converted after that. The point here is that this is anywhere between 6 months to 2 years, right, to get to that point. And so you've built a moat around you and the customer that they're not just going to unravel that. I would describe it as being very engaged, but we're not quite married yet, is really what the LOI really means. And so we're just in the process of filling out our LOIs that are, if you look at this slide, we want to build out our LOIs so that we can then redistribute the material and create some commercial tension with that LOI rather than just jumping straight into a commercial contract straight away. So there's a bit of commercial sportsmanship around this in terms of how we want to convert to binding contracts at the right time. We have agents working for us all across the globe. There's a significant demand right the way through. I won't go through all the pricing there, but it's there for anybody that wishes to see. 70-odd% margin, $300 odd million free cash. You can see here, I think the pricing, in US dollar terms, we're talking sort of $6.50 operating cost, net of byproduct credits for a $25 per kilo sales price. So the margin's quite healthy, and that's not considering the production tax credit that His Excellency mentioned earlier today. We do have these certifications around ESG. I won't go too much into that. I think we all understand this stuff. The strategic investment we've covered are in terms of 5% stake with Orica, and we're also working with an expansion project in North America with them, what we call Alpha HPA, which is another plant that we're looking to build. And then finally, we have this downstream value add piece that is all around making synthetic sapphire using our material. Synthetic sapphire is a material that comes from HPA, and when you wafer that into wafers, which is then used for that gallium nitride on sapphire semiconductors. So we're sort of moving down the value train
in terms of entering into producing actual wafers for that power semi market. Little quick bit of corporate snapshot. I think it's good buying at the moment. So Chris is giving me the wind up. I've got 10 seconds, so that's about it. So I think I've managed to smash it out. I hope that was like fire hose for you all. So thank you very much.